an object of mass 5 kg falls from rest. A vertical distance of 20 meters and attains a velocity of 10 meter per second. The question is to find how much work gets done by the air resistance on this object. So we have to take G is equal to 10 meter per second squared. So here, this is a question directly from the work energy theorem. So work energy theorem says that work done by all the forces acting on a body is equal to the change in its kinetic energy. Very simple. Okay, so now what are the work done? What are the works that get done on this object which is falling? One work is its mass into the gravitational uh, force, right? So because of the gravitational force, we have one work done. And second work done is the work done by the air resistance, right? Should be equal to the change in the kinetic energy half mv square. So we can write one equation. Okay, so we just have to understand that what we are doing here. So let's write one point here. This is, we want to apply the work energy theorem. So what's the work energy theorem? Let's write once for our reference. The work done by all the forces acting upon a body is equal to all the forces is should be equal to the change in the kinetic energy. The kinetic energy of the body. All right, so now I'll write mg for its mass into the gravitational acceleration due to gravity. So plus the W air has to be equal to energy. Kinetic energy is given by half of m into velocity squared, right? So now what is unknown here? Unknown is the W air. So this is what has been asked. This has to be equal to now half mv square minus the work done because of its m into g. All right, let's substitute. So this is half. The mass is given 5 kg. V square. V square indicates its final velocity. Okay, so it attains the velocity of 10. So 10 squared minus the work done because of its gravity is nothing but what is weight? It's m into g into h. Work done by an object, right, which falls at a distance, falls a vertical height of h is nothing but mgh, right? Because work done is nothing but force into distance. What is the force? M into G. What is the distance? H. So it has to be mgh now. So just remember this. This is m into g into h. So mass is once again 5 into g is 10 into height is 20 meters. It covers a distance of 20 meters. This is what they say. So, right? I think when we substitute this in the calculator, this is 250 minus 1000, that is minus 750 joules. All right. Another question. The displacement of an object under the influence of certain force at time t has a has an equation that t is equal to root of x plus 3. So calculate part A of the question, displacement. The displacement when velocity is equal to 0. Part B of the question, work done by the force in the first 6 seconds. Okay, so let's consider that what they have given. All right, they have given that the value of t is equal to root of x plus 3. Convert this into x. So root x is equal to t minus 3. So this means x is equal to t minus 3 whole square. All right, now this is the displacement. X is nothing but the displacement. They mentioned that displacement is given and the time. The relationship between displacement and time is this, which means x is the displacement, t is the time. Okay, so now I need the displacement to get the velocity. Find the displacement when velocity is equal to 0, correct? So what is the velocity? Velocity is the differentiation of displacement with respect to time. So dx by dt, so this is 2 times t minus 3. Okay, I got the equation for velocity. So when you have the equation of velocity, I can find out the displacement when velocity is equal to 0 means, right? This is the part A answer. Velocity has to be equal to 0. So 2 times t minus 3 needs to be equated to 0. This means t is equal to 3 seconds. right? Anyway, 2 will cancel. T minus 3 is 0 implies t is equal to 3 seconds. Okay, so find the value of x when t equal to 3 is the question. So they said that x is equal to t minus 3 the whole square. So put 3 over there. So this is 3 minus 3 whole square. So this is equal to 0, right? When velocity is 0, even the displacement is equal to 0. That is the answer to the first part of the question. To answer the part B, right, let us calculate the velocity because we need the change in the velocities later, right? So first find the velocity at t equal to 0. When I put t equal to 0, this is 2 times 0 minus 3. So that is minus 6 meter per second. So then the velocity at t equal to 6 because 6 is asked. So this is 2 into 6 minus 3, that is equal to 6 meter per second. So now I have to simply apply the work energy theorem to proceed. So that is the work done is equal to change in the kinetic energy, delta K, right? So that is half m into final velocity square minus half m into initial velocity square. So we can simply write half m into vf square. Vf square, final velocity at 6, it is at t equal to 6, velocity is 6, so 36, minus at 0, it's minus 6 square is once again 36. So anyway, irrespective of what is half m, answer is equal to 0. So work done, right, by the force in the first 6 seconds is going to be 0. Let us move further. The next topic is called as the potential energy. All right. So we try to define this now. So the amount of energy possessed by a body due to its position is called as the potential energy, PE. So let us consider an example. There is a block attached to a compressed spring, or even it may be an elongated spring. So you see, because of the spring which is attached to the mass or a body is elongated or compressed, it's going to have some amount of energy, right? As soon as you release, there is a tendency to do work. So you have energy over there. So that block has a capacity to do work, right? So that's why it is called as the potential energy of that particular body, because it has potential to do some sort of work, right? Let us consider a stone when released from a height. Okay, so we release a stone from certain height that also had some amount of energy so that it can travel all the way down, right, to because of the gravitational potential energy, right? Again, another good example in electrostatics is two charged particles kept at certain distance, because depending upon what type of uh, charges they possess, either they repel or they attract. So there is a potential to do the job. So all these are examples of potential energies. Now, so let us try to look at the feature of the potential energy. Right now, so the potential energy is defined for conservative force fields only. This is an important point. The potential energy is defined for conservative. So we had defined conservative, non-conservative fields, out of which we already have discussed the point there, saying that, right, the conservative force systems have the concept of potential energy, whereas the non-conservative do not have the concept of, right, what is called as a potential energy. So the same point we are writing here in a different form. Now we can consider, now we can actually calculate the change in the potential energy of a system, that is using the conservative force systems. All right, let's try to write an equation now that the change, the potential energy, so I will denote this as du of a system corresponding to a conservative force, right, is, say, du is equal to negative of the force dot the dr. Anyway, force into distance is actually minus of dw. So let us try to do an integration over here, starting from a position I to the final position F. du has to be equal to, this is negative of, starting from the initial value of r to the final value of r, because with respect to r we are integrating here, that is dr. All right, so this is F dot dr. So in other words, we can also rewrite the equation in a different format over here. That is, the change in u, that is delta u, should be equal to u final value minus u initial value. This itself is what we have written earlier. So I'll write once again. This is integral minus of Ri to Rf. This is F dot dr. So basically what we do, we generally choose a reference point at infinity and assume the potential energy to be zero over there. All right. So Ri, right, you can take the initial position as infinity so that Ui becomes equal to zero. Right. So this is also important. How you define the potential energy? It is by using the following concept. Right. So if, say, Ri is equal to infinity, this is infinity, implies the ui initial value to be zero. So the potential energy at a point is defined as negative of bringing from infinity to the current position r, the F dot dr. This itself is minus of the work. Right? So potential energy of a body or a system is the negative of the work done by a conservative force in bringing it from infinity to the present position. Right, at infinity this is considered to be zero. That's why we are saying that if you are bringing an object from infinity to the current position, that negative of that itself, right, negative of that work done itself is the potential energy of the particular point. Okay, so This we'll see again and again in the electric field, gravitational potential, etc. Many points we find out the same. Okay, so let's write the actual meaning of this equation. So this implies the potential energy of a body is negative of the work done by the conservative force in bringing it from infinity to the present position. Okay, so that's a meaning of the equation. So basically, whenever we calculate the potential energy, the value depends upon where you are measuring. In the sense, what is the frame of reference? That's the first thing we need to remember. And also, if there is a conservative force F and a what you call potential energy associated with that force denoted by U, right? Then we can actually use that above equation to find out the equation of F. Okay, F and U we can try to find using this equation. I'll write that. So that is, so since U is equal to minus of integral F dot dr, this implies, which means that if I want to find F, I have to perform the differentiation, right? Take the minus to other side and differentiate. So this implies the force can be found directly by doing du by dr, or even du by dx, because anyway variables are fine, we can actually interchange the variables as we want. Okay, so basically we can do this. So this is the first or the fundamental definition of the potential energy. Now we'll move on to the types of the potential energy. Potential energies do exist in nature in variety of types. So the first type of the potential energy that we are going to see is called as the elastic. The elastic potential energy. So anyway, this is directly related to the spring force which we consider earlier, right? If there is a spring which is either compressed or elongated, which means there is a energy associated with that. So the work done by a spring force, right? This is also we have discussed. It is equal to minus of half into kx square. Already we have discussed where the spring is stretched or compressed by an amount x from its unstretched position. Okay, so let's just try to write that. This is elastic. So directly I'll write this is related to the spring force. So we know something. Let's write that point directly. The work done by a spring force is minus of half into kx squared. So what is k? K is called as the spring constant. And what is x? X is the spring's moment measured from the unstretched position. So how much it actually has moved from its unstretched position is this. So it says that, right, negative of the work done, right? So the potential is equal to, so according to the definition, U is equal to minus W. So this is minus of half kx square, right? So the potential energy of a string is given by half of kx square. Important. Okay. The next type of the potential energy which we are going to consider is like this. It is called as the gravity. The gravitational potential energy. So here, now in order to measure the gravity or the gravitational potential energy, we need two different objects of certain masses, right? So the gravitational potential energy of two masses m1 comma m2, and you need to have two masses and they have to be separated by certain amount of distance. Okay, so m1 m2 separated by distance. Distance r, okay, is given by, let's measure this u is equal to a negative value minus g into m1 into m2 divided by r. Okay, so m1 m2 and r we know, so here g is called as the gravitational constant, and its value is fixed, always 6.67 into 10 to the power minus 11 Newton meter square per kilogram. Okay, so this is the direct calculation of the gravitational potential energy between the two objects. But now let us say that there is a body of mass m raised to a height h from Earth's surface. Then you can find out how much is the change in the potential energy of the system with respect to Earth and the body, right? So that also we can measure. So this is again under the same gravitational potential we'll measure. So, okay, yes, I do. If of mass m raised to height h from the Earth surface, this implies the change in this delta U is equal to this equation mgh divided by 1 plus h by r. right? So here the capital R is the radius of Earth. Radius of. Now you see, if the H value is very small compared to R, that is, H is much, much less than R, then I can say that the potential energy is equal to M into G into H. So this is the equation which we were using earlier. Okay, right? This is applicable only when H is much, much lesser than R, like 10 meter, 20 meter, 50 meters are very negligible compared to the size of the whole Earth. Okay, then we have another potential energy that is coming into picture, and that energy is referred to as the electric potential energy. Right. So electric potential energy is always measured uh, between the two charges, right? So electric potential energy of two charges, say Q1 and Q2. QR is the standard notation for the amount of charge, right? Q1, Q2 separated by certain distance. Separated by certain distance, say R, right? Is given by, let's denote that as U. U is equal to, there is a constant. So this is some constant, say K into Q1, Q2 divided by R. So here the K is a constant and its value is given by 9 into 10 to the power 9 Newton meter, Newton meter per coulomb square, because coulomb is the measure of charge. So that is a constant value, 9 into 10 to the power 9. So that we can substitute over there, put the charge values, so many coulombs into so many coulombs divided by the distance between them. So as soon as we substitute those values, we will get the electric potential energy required for the given system.